Look at this image. I mean, really look at it. You see swirling clouds of incandescent gas, shimmering nebulae where new suns are being born, and a defiant twinkle of distant stars. You see the pillars of creation, a cosmic monument sculpted from dust and light, standing nearly 30 trillion miles tall. It is one of the most famous, most profound images ever captured. But what if I told you this is a photograph? What if I told you that the breathtaking colors you're seeing, the fiery oranges, the ethereal blues, the vibrant greens, are completely and utterly invisible to your eyes? What if I told you that this image, and almost every other cosmic masterpiece you've ever seen from NASA, isn't just captured, it's built? This isn't a picture of space. This is a scientific instrument. It's a data set translated into a language that our eyes can finally understand. The story of how these images get made isn't a story about photography. It's a story of engineering pushed to its absolute limits, mind-bending physics and meticulous data manipulation, all designed to do one thing: to let us see all the way back to the dawn of time itself. And so, how do scientists create these cosmic masterpieces? How do they turn invisible light into a portrait of the universe? The answer is going to change the way you look at the night sky and these images forever. Our journey starts with a fundamental problem, a limitation so profound it has shaped all of human history. Our eyes. The human eye is a biological marvel, no doubt about it. It's a finely tuned instrument for survival on a small, rocky planet orbiting a yellow star. It sees a specific, narrow band of light we call the visible spectrum. For our ancestors, this was perfect. It let them spot ripe fruit, see predators in the tall grass, and navigate by the light of our sun. But the universe doesn't care about our survival. It operates on a scale our biology was never meant to comprehend. The visible spectrum, all the colors of the rainbow, is a laughably tiny sliver of the full range of light that floods the cosmos. It's like trying to understand all of world literature by reading a single page, or appreciate all of music by hearing just one note. The universe is screaming with information, but our eyes are almost completely deaf to it. For centuries, this limitation bound astronomers to the ground. They peered through telescopes, their view blurred and distorted by the very air we breathe. Earth's atmosphere is a turbulent, shifting ocean of gas that makes stars twinkle. Try to see through it is like trying to read a book at the bottom of a swimming pool. The words shimmer and warp, and the finest details are lost. On top of that, our atmosphere acts like a protective blanket, absorbing most ultraviolet and infrared radiation from space. So when early astronomers tried to photograph the deep sky, it looked empty. The vast, dark patches between the stars seemed to be just that, a void, a black, featureless nothingness. They were staring at what they thought was a window, but they were actually looking at a wall. The universe's greatest secrets were hidden in plain sight, veiled by light our eyes couldn't see and the air that kept us alive. To see the universe as it truly is, we had to do something audacious. We had to escape the shackles of our own planet. We had to get above the atmosphere. We needed to build an eye in the sky, and on April 24th, 1990, the Space Shuttle Discovery roared into orbit, carrying the most ambitious astronomical instrument ever conceived, the Hubble Space Telescope. Named after Edwin Hubble, the astronomer who proved our galaxy was just one of countless others, the telescope was humanity's answer to our problem of sight. Orbiting high above the atmosphere, Hubble would have a crystal-clear, unwavering view of the cosmos. It was built to see farther and with more clarity than any telescope in history. But the mission almost ended in disaster. The first images came back blurry and distorted. The astronomical community was in shock. The telescope, the result of decades of work and billions of dollars, was flawed. Its primary mirror, polished and near perfection, had been ground to the wrong shape by just 2 microns, about 1/50th the thickness of a human hair. It was a devastating, heartbreaking mistake. But what happened next became one of NASA's greatest comeback stories. In 1993, astronauts on a daring servicing mission installed a set of corrective optics. Basically, a pair of precisely engineered glasses for telescope. And it worked. Suddenly, the universe snapped into focus. Blurry smudges became dazzlingly sharp spiral galaxies. Fuzzy dots resolved into brilliant star clusters. Hubble was reborn, and the era of modern space astronomy had truly begun. With its vision fixed, Hubble turned its gaze to one of those empty patches of sky, a speck in Ursa Major, so small it was like looking at a grain of sand held at arm's length. For 10 straight days in 1995, Hubble just stared, collecting every single photon of light it could. It took 342 separate pictures, letting the faint, ancient light build up on its detector, one particle at a time. The result was an image that fundamentally altered our place in the universe. The Hubble Deep Field. What was once a patch of pure blackness was revealed to be a celestial tapestry woven from light. The image contained nearly 3,000 objects, and almost every single one wasn't a star, but an entire galaxy. Some were the most distant and youngest ever seen at the time. It was like taking a core sample of cosmic history. It proved the universe wasn't empty, but was teeming with galaxies in every direction. We weren't in a lonely galaxy in a vast void. We were in a cosmic metropolis, a universe overflowing with worlds. And this revelation was all made possible by a hidden process of turning raw data into scientific ARTITA SO. How did Hubble, and now its successor the James Webb Space Telescope, actually create an image like the deep field? The first thing you have to understand is a crucial, mind-bending fact. Telescopes like Hubble and Webb don't take color photographs. They're not like your phone camera. In fact, they only ever take pictures in grayscale. The process is way more intricate and scientifically deliberate than just snapping a photo. A telescope is basically a light bucket, designed to collect as many particles of light or photons as possible. Its camera, a CCD, is just a grid of pixels that counts how many photons hit each spot. More photons, brighter pixel. That's it. You get a grayscale map of light. TO create the vibrant color images we all know. Scientists use a trick that goes back to the dawn of color photography. The telescope takes multiple pictures of the same object, but each time through a different filter. Think of them like colored sunglasses. One filter only lets through red light, another only green light, a third only blue. This gives them 3 separate grayscale images, one showing where it's red, one where it's green, and one where it's blue. Back on Earth, scientists take these 3 black and white images and assign their corresponding color in a computer. The red filtered image is colored red, the green filtered one green, and the blue filtered one blue. Then they're stacked together. When they're combined, they create a single full-color composite image. This is what we call a true color image, and it's a pretty close guess of what our eyes would see if they were as powerful as Hubble's. But here's where the real magic begins. Hubble and Webb aren't limited to visible light. They can see light that is completely invisible to us, ultraviolet and infrared. And this invisible light carries some of the most vital secrets of a universe. To show it to us, scientists use what's called representative or false color. The principle is the same. Take multiple grayscale images through different filters. But now, the filters aren't just for red, green, and blue. They might isolate specific wavelengths of infrared light, or even the light emitted by a specific chemical element, like glowing hydrogen or superheated oxygen. Since this light has no color we can see, scientists have to assign one. They follow a consistent rule called chromatic ordering. The longest wavelength of light they capture gets assigned to red, the middle wavelengths get green, and the shortest get blue. This is an artistic choice. It's a scientific translation. The colors in an image, like the pillars of creation, aren't fake. They are a visual representation of real physical data. The searing red might represent the glow of sulfur atoms. The green could be mapping hydrogen gas, and the piercing blue might be tracing superhot oxygen. By assigning these colors, astronomers can instantly see the chemical makeup of a nebula and understand how these gases are interacting. The image becomes a chemical map, a story of cosmic creation told in a language we were never meant to see, but that we have learned to translate. Before any color could be assigned, before that beautiful composite is ever built, the raw data beamed down from the telescope has to be meticulously cleaned. The universe is a messy place, and the raw images are full of glitches and noise that have nothing to do with distant galaxies. As the telescope stares into space for hours, it's not just collecting light. It's being bombarded by high-energy particles from space called cosmic rays. When a cosmic ray zips through the detector, it overloads a few pixels, creating a bright white streak. If you didn't fix this, a deep field image would look like it's been sprinkled with digital snow. Scientists use clever algorithms that compare multiple pictures of the same spot. The stars and galaxies stay put, but the cosmic ray hits are random. The software finds these random bright spots and digitally erases them, cleaning the image pixel by pixel. Then you have satellites and asteroids that can drift through the view during a long exposure, leaving bright trails that also need to be removed. Even the telescope's camera isn't perfect. Some pixels might be hot and always appear bright, or dead and never register light at all. The science team has a map of these bad pixels, and they are corrected by averaging the values of the pixels around them to get a really deep view of the universe. Telescopes take hundreds of exposures of the same patch of sky. For the Hubble Deep Field, it was 342. These individual images have to be perfectly aligned with each other, down to a fraction of a pixel, using the stars as anchor points. Once aligned, they are digitally stacked. This is where the magic happens. The real light from a distant galaxy, the signal, is in every frame, so it adds up and gets stronger. All the random electronic noise gets averaged out and becomes weaker. What you're left with is a single, deep, incredibly clean master image for each filter. This painstaking digital janitorial work is what transforms a noisy, corrupted dataset into pristine canvas for the final masterpiece. For 3 decades, Hubble totally revolutionized our understanding of the cosmos. But even Hubble has its limits. It's primarily an optical and ultraviolet telescope. It can see a little bit of infrared light, but it's blind to the longer infrared wavelengths where the secrets of the very first galaxies are hiding. This all comes down to a property of our expanding universe, redshift. As the universe expands, it stretches the fabric of space-time itself. Light from the most distant galaxies, which has been traveling for billions of years to reach us, gets stretched right along with it. Visible and ultraviolet light that was emitted by the very first stars over 13 billion years ago has been stretched so much that by the time it reaches our solar system, it arrives as infrared light. This is a cosmic dawn, the era when the first stars ignited in the darkness after the Big Bang. To see this moment, to witness the birth of first light, we needed a new kind of eye. We needed a telescope designed specifically to see this faint, ancient, redshifted infrared light. One with a much larger mirror to collect more of this light, and one that operated far from the heat of the Earth, which itself glows in the infrared. This was the vision for the James Webb Space Telescope, or JWST. It was an engineering challenge of breathtaking audacity. It would have a massive 6.5-meter primary mirror made of 18 gold-plated hexagons, giving it over 6 times the light-collecting power of Hubble. This giant mirror had to be folded up like origami to fit inside a rocket, then unfold itself perfectly in space. And to see in the infrared, Webb had to be incredibly cold. Any heat from the scope itself would blind its sensitive detectors. So, it was designed with 5-layer, tennis court-sized sun shield to block heat from the sun, Earth, and Moon. Finally, it would be sent not into Earth orbit, but to a special point a million miles away called L2, where it could stay frigid and have an unobstructed view of the deep universe. Building it was a technological gamble on a colossal scale, but if it worked, it wouldn't just be an improvement on Hubble. It would be a time machine that on Christmas Day, 2021, the James Webb Space Telescope launched. After a flawless journey and a nail-biting, month-long deployment, the telescope cooled down and opened its golden eye on July 12, 2022. The world saw the result. The first image released was Webb's first deep field, and it was transformative. Where Hubble had taken over a week to produce its legendary deep field, Webb achieved an even deeper, sharper, and more detailed view in just 12.5 hours. It was a stunning demonstration of power. The image revealed thousands of galaxies, a sea of jewels scattered across black velvet, but the details were staggering. We saw tiny, faint, red smudges that had been completely invisible to Hubble, galaxies from the universe's first billion years. We saw gravitational lensing, where the immense gravity of a foreground galaxy cluster was bending and magnifying the light of even more distant galaxies behind it. Comparing Webb's images to Hubble's of the same objects shows a profound difference. Take the famous pillars of creation. In Hubble's visible light image, the pillars are dark, opaque towers of dust. But in Webb's infrared view, the dust becomes translucent, almost ghostly. We can peer right through the veil and see hundreds of newly formed, glowing red stars that were hidden before. The pillars are no longer just structures. They are active stellar nurseries. It's not that Webb is better than Hubble. They are complementary. Hubble sees the glowing surface of the gas clouds and visible light, while Webb sees the engine of star formation happening deep inside them in infrared. It's like having both a regular camera and an X-ray machine to study the same subject. Together, they give us a complete picture. Webb is pushing the frontiers of observation right back to the edge of the cosmic dark ages. And every single revolutionary image is built the same way, by translating invisible infrared data into a language of color we can finally see. The process of colorizing these images is a delicate dance between scientific accuracy and clear communication. The image processing specialists who build these images are both scientists and artists. Their job is to take the raw, black and white data and create a final image that is not only beautiful, but also scientifically meaningful. Let's say Webb observes a nebula using 6 different infrared filters. This gives the team 6 separate, high-resolution grayscale images. Each image highlights different features. One might be sensitive to the glow of hydrocarbons, another to molecular hydrogen, and another to heat from fine dust. The first decision is how to assign colors. Following the rule of chromatic ordering, the filter that captures the shortest wavelength of light is assigned blue. The next filters in the sequence are assigned to shades of cyan, green, and yellow. The filter that captures the longest wavelength is assigned red. When all 6 of these colored layers are combined, they produce a rich, detailed, and scientifically intuitive image. An astronomer can look at it and know, just by the color, that the red areas are showing things associated with longer wavelength infrared light, like cooler dust, while the blue areas are tracing shorter wavelength phenomena. There's also a compositional element. Since there's no up or down in space, the team can rotate and crop the image to create the most compelling view, drawing the viewer's eye to the most important features. This isn't faking the data. It's about presentation, just like a nature photographer framing a shot to best capture the majesty of a mountain. But the raw data from Webb is so sensitive that the initial files often look almost completely black. That's because the dynamic range, the difference between the faintest and brightest parts, is enormous, far greater than a computer monitor can display. A huge part of the process involves mathematically stretching the data to bring out the faint details in a dim nebula without completely blowing out the bright stars. It's a careful balancing act, all done to reveal the treasure trove of information hidden inside the data. The final product is a symphony of light and color, where every hue is tied directly to real, physical information, translated for our eyes to behold. These images are so much more than pretty pictures. They are revolutionary tools that have rewritten our textbooks. By capturing light from different eras, Deep Field from Hubble and Webb act like a family album of the universe. We can see galaxies at all stages of development, from the small, messy infant galaxies that formed just after the Big Bang, to the majestic spiral galaxies of today. We can literally watch how galaxies merge and collide over billions of years. These images have also helped us map the large-scale structure of the universe, a vast, filamentary network called the cosmic web. In many of these pictures, you can see strange, distorted arcs of light. Those are distant galaxies whose light has been bent and magnified by the gravity of a closer galaxy cluster, a phenomenon called gravitational lensing. By studying how the light is distorted, astronomers can calculate the mass of the foreground cluster. And the result is always the same. There's far more mass than we can see. These images provide some of the most direct evidence we have for the existence of dark matter, the mysterious substance that makes up about 85% of the matter in the universe. And perhaps most profoundly, these images give us a sense of our place in it all. The Hubble Deep Field revealed thousands of galaxies in a tiny speck of sky. Extrapolate that across the entire sky, and it implies there are some 2 trillion galaxies in the observable universe. Webb's discoveries show that planets are incredibly common. When you multiply the trillions of galaxies by the hundreds of billions of stars in each one, the numbers become staggering. We haven't found life yet, but these images show us that the universe is filled with an almost infinite number of potential homes. We start with a simple question about a single image. how is it made? We've journeyed from the limits of our own eyes to the very edge of the observable universe. We've seen how decades of engineering and a relentless pursuit of knowledge allowed us to build eyes in the sky. And we've uncovered the secret science, that these aren't photographs but complex data constructions. They are mosaics of grayscale images, meticulously cleaned and then translated into color. We've learned that the colors are a language, a way of visualizing invisible light, to map the chemical makeup of the cosmos. This process doesn't make the images fake. It makes them more real. It reveals a universe that is richer, more complex, and more beautiful than our senses could ever imagine. We pointed our most powerful instruments at a patch of sky we thought was empty, and we found it was full of creation. The next time you look at one of these cosmic masterpieces, remember the hidden story. Remember the decades of work, the invisible light, and the scientific translation that allows you to witness the birth of stars and the dawn of time. Remember that you are not just looking at a picture. You are looking at a discovery. You are looking at a universe revealing itself. The James Webb Space Telescope has an estimated 20 years of observation time left, promising a future filled with even more incredible revelations. What discovery do you hope Webb makes next? Let us know in the comments below. And if you want to keep exploring the biggest questions in the cosmos, make sure to subscribe and turn on notifications. The universe is waiting.